All right, well, welcome back to day number 2 here in vector calculus. And today we're going to basically continue our discussion that we were doing last time, looking at vector valued functions. So we did a little bit of review on just the vector operations, how they work and what they do. And then I introduced you to vector valued functions, which are just functions that we plug in a number and we get out a vector. Pretty basic, pretty straightforward. But now that we've talked a little bit about them, looked at how we find the domain, the limits, things like that, well, now we'll start going into the calculus. All right, so any questions on the homework or anything at this point? No, we're good? All right. Well, then I'm going to go ahead and switch my view so that we can go to the whiteboard.
All right, so hopefully this will work a little bit better for us. Today we'll be able to see the screen a little bit better. Using my phone camera, it's a little bit better than my computer camera. Saw that this worked pretty well for my earlier class. So we're gonna go ahead and give this a ride and see how it goes. Just let me know if you have any issues seeing or anything like that. All right, so last time we talked about vector valued functions. So let me just sort of bring those back up here. So again, remember, I'm going to write them as VVF for short. And again, they are just functions that we plug in a t and we get out a vector. And so for us, sort of our generalization, excuse me, was that we made these functions f, g, and h, and use that as basically the component functions. And we saw that in terms of limits, it all came down to component functions. Well, same thing is going to be true about everything else that we do. All right, so these are vector value functions. In terms of the domain, you remember what we have to do when we find the domain of one of these?
Distinguish each domain for each function inside, and then determine what's going to be the overall domain.
All right, and then how do we figure out the overall domain once we have the domain of the three individuals?
I don't know how to put it into words.
Can anyone help Bradley out?
The domain is the intersection of the domain of the component functions.
Yeah, so we look at the intersection of them. We look for the overlap of the three domains. So I'm just going to put here the domain. This is the intersection of the domains of the components. Right, and then I see Victor put in there chat box, he said, look at each restriction. So basically, yeah, you look at the restrictions on F, the restrictions on G, the restrictions on H, and then you make sure that you account for all of those. And then that's the intersection. All right, so we got that. And then we looked at the limit. And the idea here, we're taking a limit as t approaches some value, we'll call it c, r of t, and it does equal a vector. Just to be generic, I'll call it a capital L for limit. So it's my limit vector. And this limit vector, basically it's found by finding the limits of each of the component. So we did one last time that involved a little L'Hopital's rule and stuff for practice. But basically, we're doing exactly the same thing we did for just regular old functions. We're just doing it multiple times, one for each of these guys. All right, so that's where we got. I do want to mention one thing. You may remember that we had an epsilon delta definition of limits. You remember that fun thing where it was for every epsilon greater than 0, there's a delta greater than 0, such that f of x minus L is less than epsilon when x minus c is less than delta. Okay, so yes, we get the sad face and everyone's like, yeah. All right, you can do the same with vectors. We're not going to, don't worry. I'm not gonna do that to you, but you actually could easily do it the same way. And what we would say is like the limit as t goes to c of r of t equals L, we just be looking at r of t minus L. The difference in those two has to be going to 0. So instead of the absolute value, what you'd actually do is you'd do a magnitude, right? So this is the difference in those two vectors. The magnitude of the difference in those two vectors has to be less than, pick your favorite value. And then, given that t minus c is less than delta, so don't worry, I'm not going to test you on this. We're not going to do homeworks on it, but this is what the structure would look like. And if you kind of recall your epsilon delta stuff, you can see that this looks very, very similar. We just have to adjust it slightly because of the fact that we're dealing with vectors. Anyway, all right, so that's the idea behind limits. Now, once we have limits, this is where we can now start turning our attention to things like continuity and derivatives and so on. So let's go to continuity of these guys. But I want to open up with, what do you remember about continuity of regular functions? Like, what do you need for a function of just one variable, good old normal function, to be continuous? Remember anything?
It can't have any breaks.
Okay, so there can't be any kind of
or
breaks or holes, things like that. You can have case. You have those sharp turns. That's okay for continuity, but not for differentiability. Well, there were 3 things that had to happen. So this is just for continuity of regular functions. And I'm going to put regular in quotes. Just because that's what we think of as regular functions. So there were things we definitely had to avoid. We had to avoid holes. We had to avoid asymptotes. I saw that Victor put in here. Hold on a second here, guys. Can you still hear me?
It's a little faint, but yeah.
All right. My wireless earbuds just died. Hold on 1 second. All right. Is that better?
Yeah.
Yeah, that's perfect.
Yes, maybe, yes. Okay. Except it just told me goodbye. I'm going to pause the video real quick. All right, so as I was saying before I kind of got cut off with the technical difficulties, there were definitely things we had to avoid. Asymptotes, holes. Victor put in the chat something about the limit has to be equal on both sides, getting at the idea of like a jump, right? There were all those things that we had to avoid. But when we technically were talking about continuity, these 3 things had to happen, all right? The first was that the function has to actually exist there. that eliminates asymptotes, that eliminates holes, right? But we also needed for the limit to exist. That takes care of things like jumps, right? All those kind of weird things. But then we actually needed one more thing, which was that the limit has to actually equal the function value there. And what that eliminated are those kind of weird situations where you've got a limit existing, your function does exist, so there's a dot, but there's a jump as you go from one to the other. So that's why you need the third one. And sometimes you'll see in a text just this third one. And I think the reason that you'll see that, and Jacob, I'm just muting you because sometimes it's switching to your view. I just don't want you being on the screen so people can see it on the recording. So no offense. But anyway, this third line is basically saying the limit has to exist, the function has to exist, which kind of covers 1 and 2. But anyway, these were the conditions for continuity. Basically, everything was nice. Now, for vector value functions, this is a little bit more difficult to think of in terms of the picture, because what does the picture of a vector value function look like? Well, we'll talk about that a little bit more, but in reality, think about what's happening is you plug in a C and you get a vector. You plug in another value, you get another vector and another vector and another vector, right? So you're just getting a whole series of vectors. What does that even mean to be continuous? It's not like we can go with the, right, draw it, not lift up your pencil kind of thing, right? So Victor says, is it a 3-dimensional shape? Kinda, but it really is just a series of vectors. And so continuity as a concept of it just all runs together doesn't really make sense. But what we can do is take this exact definition and extend it to vector value functions. So the first thing that we're going to need is that the vector valued function exists at that point. Okay, cool, that makes sense. So at C, there is a vector. There also has to be a limit. So as we're getting closer and closer to C, the vectors are approaching a specific vector L. And then we just have to ensure for continuity that these things are equal to each other. So there's a one-to-one correspondence in these things, right? These are linked together. And in fact, if you want to talk about continuity of any kind of function, because there are all kinds of functions out there in the world, and we'll see some more as we go in this quarter, this is what it's always going to mean for them to be continuous. That the function exists, the limit exists, and those two things are equal to each other. All right, so we know how to evaluate a function. We know how to find the limits of these things. So you should be able to see if those two vectors are equal and then thus be able to talk about continuity. Now, what it really comes down to, since these vectors are built from components and those components were regular functions, an alternative way of checking continuity that's kind of faster is we know that a vector value function is continuous when all the component functions are continuous. So just like with limits, where we did it multiple times, right? Like we're going to evaluate the limit of each of the component functions, or domain, we look at the domain of each of the component functions. Well, same deal here. for continuity, you're just going to look at continuity of each of the component functions. And wherever all three of them are continuous, the vector value function is also continuous. All right, so no big deal, but we definitely need to know about continuity before we can move on to differentiability. All right, so any questions at this point? I think we still have to discuss the graphing, right? Because people are asking if it's a three-dimensional graph and all that. So I think we'll address that next, but any questions about continuity itself, like the definition? Are we good? Thumbs up? All right. Okay, so let's talk graphs for a second. Now, I'm going to look at a two-dimensional vector value function, just because it'll be a little bit easier to draw its graph, because I can draw a vector, a 2D vector on the whiteboard. I have a hard time representing 3D vectors without, you know, extra stuff. So let's just talk about the graph of one of these things, and we'll use a specific vector valued function as an example. So let's look at, say, r of t equals t comma t squared. So super easy. And I know you all have this written. I'm going to change it slightly. I'm going to make it t plus 1. All right, so what I'm going to do is basically make a t-chart like you're really used to, where we've got some t values. Let's go say -2, -1, 0, 1, and 2. And on the second column, we're going to have what our vector is. So super easy, right? We just plug in the values. So we get here -1, 4. Then we get 0, 1, 1, 0, 2, 1, and 3, 4. So you know how to plot those vectors. We'll go ahead and do that over here. And we're going to plot them just like you always plot them, but we're going to start with their tails at the origin. And then their heads are going to be, you know, off wherever the vector tells us to go. So if we start at the origin, we do -1, 4. That's up here. So that would be the vector for t equals -2. Okay, then at t equals -1, we get the vector 0, 1. So that looks like that. Then we get 1, 0. Then we get 2, 1. And then we get 3, 4. All right, so that's the graph of those 5 values. But obviously, as the t's go between -2 and -1, or between 0 and 1, we're going to get more vectors, right? Like, let's just think about the ones between t equals 0 and t equal 1. T equals 0 was this short little guy pointing to the right. T equal 1 was the 2, 1. And as we were to go, if we were to plug in a half, 0.1, 0.96, all those different values, we get a whole string of arrows that kind of go between those. So let me, just for the sake of having them here, right? We're going to have all kinds of arrows. And so it does start kind of looking like it's getting shaded in, right? But this is really convoluted. It's hard to see the specific values for those arrows. So instead, what we do is, instead of drawing the arrows, we're just going to draw the point that's at the end of the arrows. that's out at the arrowhead. Right, so like think about this vector that was -1, 4. Instead of having this arrow, I'm just going to put a dot right here. And this would be when t is equal to -2. Now, that green dot is not the vector value function. What it's telling us is where the arrow ends. Okay, so basically this is not from our graph, but if I were to say, let's say there was a dot here, what that dot actually means is that there's a vector that runs out to that point. This is mathematicians being lazy, right? Like we do this all the time. You are very familiar with that we try to go shorthand, try to do as little as possible. Why bother drawing the entire arrow if all you have to draw is the point at the end? That's enough information. It still tells me everything. It's just way faster. So if we were to do that, let me erase our vectors that we've gotten so far. And instead, let me just draw in the dots. So for that vector 0, 1, its end was up here. 1, 0, its end was over there. The 2, 1 was over here. The 3, 4 was over there. And now, if we were to look at those between 0 and 1, and all we took care of were the dots at the end of the arrows, we start seeing something like this. And you could continue doing the same thing for all of them. And what we end up seeing is a parabola. So the collection of all the points at the end of these vectors forms that parabola. But the vectors themselves, go ahead, Bradley.
Is that because of the t squared as a component, or is that just, it just happens?
Yeah, it's totally because of this. I'll show you in a second. Right, but these would be all the different, or a set of different vectors from this thing. They're just running from the origin somewhere to that blue line, depending on the t. So notice that this 2D vector valued function, even in its graph, it's still two-dimensional. It's still two-dimensional. It's just we don't end up representing the vectors themselves. We just look at the points at the end. All right, now this one is a parabola because of the structure of this. If these component vectors were, or component functions, I mean, were defined in different ways, shape could look completely different. But basically, we're just keeping track of where the ends of the vectors are. Minus the vectors, like you take away those red arrows. Is this reminding anybody of anything? Because it should. You've seen something like this in calculus.
Tangents?
No, not tangents.
Secants?
Where you define x and y in terms of some other variable.
Parameterization?
Yeah, so these are parametric equations in essence, right? Like think about it. This is saying x equals t plus 1 and y equals t squared. It's the x component, it's the y component. And so the graph of the points that form the very tips of the arrows, that's the same as the graph of this parametric equation. So there is a difference. I want to make sure you guys understand. There is a difference here because the vector value function itself is not that blue line. It's the collection of all the vectors that run out to that blue line. But if all we're going to do is graph that blue line so we can keep track of where the ends are, that's the same as the parametric curve. So very similar to parametrics. And in fact, when we draw that graph, that parametric graph to get the endpoints, it's identical. It's just, it's not those points we're concerned about. It's the vectors that point to those points that we're concerned about. Okay, so, but this then shows you why we get the graphs that we get. Like you may remember doing the parameterization, eliminating the parameter. So if we were to do that with this one, for example, we'd get that t is equal to x minus 1 from the first equation. You fire that into the second one, and you get y is equal to x minus 1 squared. Well, that's the graph of that blue line. That's why we see it as a parabola, right? But again,
Honestly,
that's just where all the vectors.
It's kind of wild.
Right, Brett. Yeah. You're going to see this happen a lot this quarter, that stuff we do that's new is not new. It's definitely related to something else that we've already done. I mean, even look at like so far continuity limits and all that. It's exactly what we did before, just multiple times. So this is going to be a common theme. Every time we run into something new, we're going to be able to relate it back to something we already did. Because we're kind of like, if you think of math as we're building the building, right? Well, we're on this level, we're just going to the next level, but we use the level that we're on right now to make that next step. And so we're going to see a lot of that. All right, so I guess long story short, when we graph vector value functions, we really are just going to graph their endpoints, which means we're really just graphing a parametric set of equations. We just remember that that's our guide for where to run our arrows to. And when there's a t value, like, you know, remember with parametrics, we would often say, well, this is at t equals minus 1, this is t equals 3, or that's just like, you still might write that, right? You still might write t equals minus 2, but that just tells you that the vector, when we're at minus 2, that's where we want to head. Okay, so there's just a little bit of an extension over parametric graphs. Okay, well, cool. When in doubt, just graph the parametrics and you're good to go. So if we kind of use this idea, though, to talk about continuity, a vector value function is going to be continuous if its parametric graph is continuous. And if you go back in time, access your memory banks, go back and look at your notes or whatever, you'll see that when we talked about parametric graphs, they were continuous when their individual components were continuous. Same deal. All right, so what's the saying? Everything that's new is old again, or something like that. Yeah, this new stuff is just old stuff. It's nothing new. All right, so now that we got graphs, let's talk derivatives. All right, it's time for me to start earning my money and actually teach you calculus. So let's look at derivatives of these things. All right, so the notation we use is going to be exactly the same. We'll either write d dt of r of t, right? Or we'll write r prime of t. So both of those notations are perfectly fine. It's very consistent with what we did before. So we'll do one or the other. And again, it's the rate of change. It's the rate of change in this vector value function. All right, so what we're gonna have to do though, all right, I have no idea what that says, Jacob. He just put something in the chat. And oh, nothing new under the sun. Yes, thank you. Oh, you went Latin on me. I see how you are. All right. Look, I'm an old man trying to read off of a screen that's far away with bad eyes, who's barely able to concentrate on math. No, that's all good. All right. So, but let's just think about it. If we're looking for a rate of change, how this thing is changing, we're going to set it up exactly the same way that we did derivatives before. It's going to be a limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t. So again, go back to what we've seen before. This is the exact same definition of the derivative that you got in the first week or two of calculus, right? Go back to last year or whenever it was. You saw the same thing except without vector value functions. So just regular functions. So we're going to do exactly the same thing. We're going to look at these and see what happens to them. All right. So before we slug it out with the algebra, let's draw a picture. Let's actually see what's going on. So here are some axes. Let me give you a parametric curve that's showing the progression of the vectors. And let's look at some specific r of t. So r of t, maybe we'll go out here. So let's say that this one is r of t. So the point here on the blue graph, that's where we are in the parametric graph when we're at t, but of course we've got this arrow. Now, if I add a delta t, I'm going to go a little bit further away. So let's just say that this right here is r of t plus delta t. So we take a little bit of a time step, a little delta t, a little increase in our variable, and we get this new vector. So then what I need to do is I need to take the difference in those two vectors. So I don't know if you remember how to do this geometrically. When you add vectors, you put them together head to tail, and then connect the original tail with the head. When you subtract, you have to turn it around, you have to flip it over, and then add it, right? So adding the negative. But when you've got your two vectors lined up like this, the easiest way is actually just to connect their heads. So we just connect these two dots. So I'll make that guy green. And then it actually points towards the positive one. So this right here is the difference in those two vectors. So that's what our top's going to look like. So then what happens when we divide by delta t? And so real quick, vector, I just did it again. I think from now on it is vector mulatto. So you just said displacement vector. It's not quite the same as a displacement vector. I mean, it kind of is. It would be the displacement vector if we're talking about a particle that's moving along this path. So kinda, but not quite exactly. Anyway, so there's our difference. And then what happens when we divide by delta t? What does that do? We'll get to that in a second, Jacob.
It doesn't do anything, right? Because delta t is so small.
It definitely does something. It doesn't change the direction, though. It's a scalar multiple. And so what it's going to do is it's going to change its length.
Okay.
right? And in terms
Does
of,
it make
does
the
it make
length
it longer?
Since
So
like
does it
delta
make
t
it
is supposed to be
longer
really
or
small?
shorter? Well, yeah, but if delta t gets small, then these two vectors get closer together. So the difference vector also gets really small, right? So, because remember, dividing by a number is going to change the length. Dividing by a small number is going to want to make it longer. But
Does it
this
make
is
it a
also
unit
getting
vector?
really, really short. So how long it is varies. Its length could actually be lots of different things. And we'll see how we can figure that out. But Jake, you know, you put in the chat, you said, is it coincidence that it's looking tangential? Not at all, right? This thing isn't a tangent vector as it is. It's getting pretty close, but you can imagine if we bring these two red ones together, that thing gets more and more tangential. And it shouldn't surprise you, because think about what we're doing. Let me draw a couple of points here on this graph that are further away from the arrows. Let's just look at the tips. Look at where the arrows are pointing. So we've got like this point and this point. And in essence, what we're doing to get that difference is we're connecting those two dots. But if we make delta t small, that means these 2 points are getting really, really close together until they're infinitesimally close. That's exactly what we saw when we did regular derivatives, right? Which ended up giving us the slope of a tangent line. So it's not coincidence, and in fact, it's just how this stuff is defined. It turns out that this guy, R prime, is going to be tangent to the parametric curve. So I'll go ahead and write that down because this is important stuff. So I'll even put a little star next to it. But R prime, the derivative of the vector value function, is going to be tangent to the parametric curve. Now, it turns out, though, that vectors that are tangent to a parametric curve, there are actually two options, right? Like I've got this green one that's pointing up and to the right, but I could also have the one that's pointing down and to the left. So it'd be really nice if we could tell which direction it points. And we can, because if you think about how this was constructed with the subtraction, it's always pointing towards the t plus delta t. And t plus delta t is somewhere next, right? It's somewhere coming up. And so not only is it tangent to the parametric curve, but I'm going to put here in the direction of greater t. So when we think about parametric curves, there's an orientation, right? You kind of are following the path in a certain track because of t. Well, it's the same idea here, that if we were to be following that as a path, the derivative of the vector value function is always going to be pointing tangent to the curve. So so Jacob just says it's like a directional tangent. Absolutely. Yep. It points you in the direction of travel and always tangent to the curve. Even better is this. Okay, well, let's just go back to, let me erase some of this stuff, clean up our picture a little bit, and let's just look at R of t, and we'll put in a vector. So here's axes, here's a parametric graph, here's our R. Let me put on the R prime. Now, again, I don't really know its length in this discussion. we'd have to know a little bit more about how this vector is getting swept through, not just where it is, but when it reaches all those points. That will determine its length. But I know for sure its direction is this way. It's tangent, and it's in the direction of travel. I'm assuming that this is a parametric curve that's doing this, right? Okay, so we know that r prime is tangent to the curve. Well, it turns out that r prime and r are orthogonal. We'll prove that later. But that's another kind of fun fact here that I'll go ahead and write as well. So this will get another star. And so what we know is that r prime t to r of t. All right. And this one, unfortunately, is not always true. So we do have to be a little bit careful here. I am going to put for special functions. But the tangent to is always the case. If you have a circle, for example, then this is always the case, right? But anyway. All right, so now that we've seen what happens geometrically, right, that is pointing tangent to the curve and all that, let's now talk about how we calculate it. And what we're going to do is our usual. Let's do it one time. Let's do it one time so that we know every single one is done exactly the same way. And I'm going to use this definition, but I'm going to go back to a vector value function with component functions. Okay, so let's say that this is our R. So we'll call it F, G, personally, because it'll take less writing. But then when we get to 3-dimension, you'll see how this works. So let's go to that limit definition. So R prime is going to be the limit as delta t goes to 0 of f of t plus delta t, comma, g of t plus delta t, minus f of t, comma, g of t, all divided by delta t. All right, so let's do the subtraction of vectors on top. So we saw last time, I reminded you that the way we do that is just to subtract components. So we're going to get f of t plus delta t minus f of t, comma, g of t plus delta t minus g of t. And again, that's all divided by delta t. Okay, so now let's divide by delta t. Well, dividing by delta t, that's a scalar. So all we're going to do is distribute it through. So we'll get the limit as delta t goes to 0 of f of t plus delta t minus f of t divided by delta t, comma, g of t plus delta t minus g of t divided by delta t. All right, so this has just been vector algebra. But now let's take the limit. So we saw last time that if you're going to take the limit of a vector value function, you take a limit of the components individually. So if we were to move that limit in here, let me just do it real quick. So we have the limit as tilde t goes to 0 of that guy f, and then similarly a limit here. Does anybody recognize this?
It's the limit definition of a derivative.
Yeah, that's just f prime.
Yeah.
What about the other one?
G prime.
That's just g prime. So when you differentiate, you just differentiate component by component. This is when you guys should all be really, really happy, because nothing is different here. We just have to do it more times. Just like the limits, same idea of limit, more times. Continuity, same idea of continuity, more times. It's really just the same thing over and over and over. So this just ends up being f prime and g prime. So I told you I wasn't going to put an h on, but you can probably see that had we had an h, a third component, there just would have been a third component with the difference quotient with h's, so it would have given us an h prime as well. All right, so really good news, guys. You now have discovered the rule for differentiating any vector value function. All you got to do is differentiate the component functions. So what do you think you do to get a second derivative of a vector value function?
Same thing.
Same thing, it's just second derivatives and so on. So second derivative will just be f double prime, g double prime, h double prime. And if for some reason you want more than a second derivative, nah, just keep doing the same thing. All right. Normally the second derivative is far enough, especially in an applied sense, right? Because we don't usually care about stuff much beyond acceleration, unless you're looking for jerk or something, which is the third derivative, but there you go. All right, so let me show you an example. It really is as easy as regular differentiation. The only issue is going to be remembering how to differentiate the various components. So let's say we've got inverse tangent of t for one of them. I'm just trying to give you things to practice here. So let's try secant of t and how about 1 over the cube root of t. All right, so there's an r. Let's get our r prime. So what's the derivative of inverse tangent?
Isn't it 1 over 1 plus x squared?
Good, except we're going to make it a t instead of x. But that's all good? Good. So 1 over 1 plus t squared. That's when we usually think of the other way, right? You think of it as an integration rule, but differentiation works. How about secant?
Secant x tangent x, I think.
Good, except again, yep, that's right. Except we're going to make them t's instead of x's, but good. Secant tangent. And then the 1 over t cubed, right? Think of that as t to the minus 1/3. So you're going to get a minus 1/3 t to the minus 4/3. And so there would be the derivative of that guy. All right, so again, beautiful thing is that nothing is different. It's just we have more of it to do. All right, so feeling good about the derivative, at least how to go about doing it?
Yeah.
I hope so. Because it is really what you learned in your first calculus class, just lots of it.
Bruce,
So-
what's the exponent on t for the derivative of the last?
It's minus 4/3.
Gotcha.
Yeah, sorry about that. It's kind of, I ran out of space. And if we were on campus, I would have gone ahead and written on the wall.
Oh, is
But-
r of t for the last component 1 over the cube root of t?
Yeah,
Okay, that's why I was confused. I thought it was 1/3.
root t.
Yeah,
I gotcha.
or t to the minus 1/2.
There. How about that? Makes that a little bit clearer, hopefully. All right, so now we see the fast way of doing derivatives, which means, what about all those other differentiation rules? Right, like you may remember things like, what if you have a scalar multiple? Right, scalar multiples we know go along for the ride. If we add or subtract, we can differentiate each one separately, and then add and subtract. And then we have things like product rules and quotient rules and blah, blah, blah. So the question is, what about those? Do all of those rules still apply? Well, what's your hunch?
Yes.
Yeah, seems like it. If all we're doing is just regular old differentiation anyway, just more often. And yeah, all the rules you know and love still apply, but there are a couple more. So because of the fact they're vector value functions, we got a few more that we have to worry about. So let's just put here rules of differentiation. All right, so the first one, if we have a scalar, so we're going to differentiate a scalar times a vector value function. It does exactly what you expect. And we can go ahead and pull that out. If you look at the definition, you can see why. Like I've got an R written up here, but imagine I multiply that by C. That just means each of these components is being multiplied by C. When we differentiate those C's come down, and then we can factor it out. So it makes a lot of sense if you look at it, that scalar multiples still do what they're supposed to do. Adding and subtracting, same deal. So let's say you have two vectors, R and V, and you're going to either add or subtract. You can differentiate them individually and then add and subtract. So that rule does exactly what you think for add and subtract. Now, what about product rule? Well, this is where things get a little bit different, because if I said, hey, we're going to multiply two vectors together, like if I say, hey, let's take R and V and I want you to multiply them, there should immediately be a question that pops up in your head.
Dot
What is
versus
that?
cross.
Yeah.
Exactly. Which one? Which multiply do you want? So we actually have to have a rule for dot product and a rule for cross product. Okay. So the question is, how do these guys play out? Well, the good news is that it is actually very much like what you're used to with the product rule. So you remember the product rule, right? You differentiate one and you multiply by the other. And so the same thing actually happens here. We're going to get R prime dotted with V plus R dotted with V prime. So the dot product rule, everything's good. Don't have to worry about it. Everything is exactly what we expect. It's fine. But then there's a cross product. And so you probably go, all right, well, cross product should still be the same, right? I mean, it's still multiplication and everything. But there is a bit of a catch with cross product. And I don't think I mentioned this last time, and I'm just curious if you guys remember. But I'm just going to tell you a fact about cross product. Cross product is not commutative. I don't know if you remember that. If you take U cross V and V cross U, you do not get the same thing. But dot product is commutative. So the beautiful thing about the dot product is you can't really mess this up in terms of just remembering to differentiate each one and dotting it with the other, because you can swap them around. But with the cross product, you definitely have to watch this. So let me give you number 4 here. Is going to be a cross product. So the question is, which one do you differentiate first, right? What order do you do the crosses and all that sort of thing? So for the cross product, it actually looks exactly the same as what I wrote for the dot product. We're still going to have R prime crossed V. And then add to that R cross V prime. But I'm just going to put a little warning here. You got to watch the order. Because if you turn just one of these things around, you're going to be off. All right. So just watch out for that. Something you got to pay attention to because of the cross product. But I do think it is kind of nice if you look at them. They are still exactly the same form that you're used to for product rule. Just watch out for the cross product.
Suppose in a homework setting, it will tell us which way we want to go, yeah?
Well, it's all determined by what's in here.
Okay.
Right, because you'll have your two vectors being crossed.
Mm-hmm.
So there already is an order to that.
Yeah.
So that order will then determine how this plays out.
Sounds good.
Okay.
At least
I just always, yeah, think about this. Notice that R and V, it was always R and V, R and V, R and V, R and V, right? Just keep that order.
Congratulations. Sorry.
That's all good, Jacob. Congratulations on whatever. So good job. But yeah, so it's always R and V, R and V. But just start with differentiate the first. Always differentiate the first and then go. So for those of you who've had me and you know how I do product rule, right? Like regular product rule, when I've got, say, f of x times g of x, and you know I set it up so I got f of x, g of x, and then I do the derivatives underneath. And then I draw that little cross multiply thing. notice that when I do it that way, I always start with f prime times g. And that's really what we're doing here, right? We're starting with r prime cross v. So if you came up with me, which a lot of you did, and you remember me doing it this way, you're doing exactly the same thing. Exactly the same thing. And this order will make sure that you're good to go. Just always start with the f. So f prime times g, f times g prime. All right. Anyway, so there's your product rules, right? We now have two product rules, one for the cross product and one for the dot product. Even though they're structurally the same, we do have two different rules. All right, so then I guess the next one would be, what about chain rule? So chain rule, when do you apply chain rule? What kind of situation has that happened?
Function composition.
Yeah, when we have composition.
Like f of g of x or something like that.
Exactly. So we're taking one function, we're plugging it into another. Okay, well, we're going to do the same thing here. So we're going to have our vector valued function. And we're going to plug another function into it. But this function is going to be a scalar function. Okay, so it's not a vector inside of a vector. It's a regular function inside of your vector value function. And the reason it has to be like this is that, remember, what we plug into vector value functions are just regular old numbers. So this thing has to be a regular number. It cannot be a vector. So it's just a regular old function. All right, now you do remember, hopefully, how to do the product rule, that we differentiate the outside function and then we multiply it by the derivative of what's inside. And that is exactly how this plays out. You're going to get f prime of t, so just the derivative of that inner function, times r prime evaluated at f of t. All right, so again, that's nice that it's still the same structure. And it means we're not learning anything new. We just have more we have to pay attention to, right? Because this derivative involves a bunch of derivatives that are all being evaluated at whatever this function is. But I think overall, this is a positive thing, that the rules for differentiation of vector value functions are the same. All right, well, there's one more thing one more property, one more thing that happens with these. And it comes to one of the things I wrote earlier about that r prime being orthogonal to r. And I want to talk a little bit more about when that happens, because I said it happens for special functions. So the question is, what are those special functions? Well, here's a theorem for you. What this theorem says, and we're going to prove this one. All these other ones I didn't prove because it's really tedious and it's just using the definition of the derivative. But it basically falls out the same way everything else fell out. You'd see that you get, say, chain rule on the first component and chain rule on the second component and chain rule on the third component, and everything just kind of works out. But this one, it's not obvious, and so I think we should prove it. So here comes a theorem. If r dotted with r is constant, then r dotted with r prime is equal to 0. So pretty easy statement. If you take a vector value function and you dot it with itself, if that ends up being a constant, then we know that r dotted with r prime is equal to 0. And I'm even going to put here, I'm going to add to this for all t. So it will always be the case. There are lots of functions, vector value functions, that will have it where r prime and r are orthogonal. Sometimes. But in this situation, they're always orthogonal, right? So remember, that's what the dot product equaling 0, that means that these guys are orthogonal. All right, so let's see if we can prove this. And what I'm going to do, I'm going to start with r prime, or sorry, r dotted with r being a constant, because this is given. And what I'm going to do is actually differentiate both sides. So let's do a d dt. So on the left, we have to use the product rule for dot products. Oh, yeah, thanks, Ralph, for asking that question. And actually, thanks, Seamus, for telling him. THM is short for theorem. Thanks. All right, so if we use the dot product rule, we're going to get r prime dotted with r plus r dotted with r prime. So if you go back and look at rule number 4 or whatever it was on our list, that's the dot product rule. So what about the right? What happens when we differentiate C?
0.
Good, Victory, we get 0. So that guy is 0. All right, well, now we're going to use the fact that the dot product is commutative. So r prime dotted with r is the same as r dotted with r prime. Those two are identical, so we can add them up. That 2 is a scalar, so I can divide both sides by 2. And we're left with what we are trying to prove. So if you ever have a function, vector value function, that when dotted with itself gives you just a number, there are no t's in there anymore, then you know that r prime is always going to be orthogonal to r. This has to be the dot product. Because check this out, if it were the cross product, watch what happens. So let's try the same thing. Let's say we've got r crossed r. If we differentiate this thing, right, using the product rule, this is no longer commutative. So I can't just combine these as 2 of the same thing. So that's why it's really important that it's the dot product. There's also another issue here. What do you get when you cross 2 vectors?
Constant.
Yeah, you get another vector. you don't get a scalar. So this couldn't happen anyway. But I want you to see what happens when we do take a vector and cross it with itself. Well, it's not commutative, but it's anti-commutative. So when you swap the order, you get the opposite. So these things are identical but opposite signs. And what you actually get is 0. So if you ever take a vector and you cross it with itself, you're just going to get the 0 vector. So that's why there really aren't any theorems that involve R cross R, because you always just get 0. What R dot R gives you is actually the magnitude of R squared. So again, I don't know if you remember this, but it's probably worth mentioning. When you take R dotted with R, you get the square of the magnitude. So these special functions where it's always orthogonal, they're going to be the ones that where the magnitude of the vector valued function is constant. So let me show you an example of one that does this, that does give us orthogonal derivatives. And we'll work it all the way through. We'll find the derivatives and we'll dot the derivative with the original function and all that good stuff. But let's just say that R of t is sine of t negative cosine of t. So let's start with R dotted with R. So that's going to be sine times sine plus cosine times cosine. Remember, the negative when I multiply by another negative gives me a positive. So this is sine squared plus cosine squared, which you all know is 1. Okay, so we have R dotted with R is a constant. So that means that R prime must be orthogonal to R always. Well, let's get R prime. So we differentiate sine, we get cosine. The derivative of negative cosine is a positive sine. So now take R times R prime. So R dotted with R prime, we're going to get sine times cosine minus cosine times sine, which does equal 0. So here's an example of one whose self dot product or whatever is constant, and we can clearly see that R prime is orthogonal to R. So when I mentioned that the derivative is going to be orthogonal to R, it does happen a lot. It's for special things. This guy, I don't know if you recognize it. Can you imagine what that might look like if you graphed it parametrically?
Circle.
What usually happens when x's and y's are sines and cosines?
Circle, yeah.
Yeah, circle. And it is. It's definitely a circle. This one, it's not like, it is a unit circle. We're not going in the usual counterclockwise starting at the positive x-axis direction. But for example, let me just show you one. Like let's do r of pi. So that's going to be sine of pi, which is 0. Negative cosine of pi is negative negative 1 is 1. So that's r. If we look at r prime of pi, cosine of pi is negative 1. Sine of pi is 0. If we were to graph those, 0, 1, of course, we're up here, right? So that's 0, 1. Negative 1, 0. And you can see for sure that those guys are orthogonal. And knowing what we know about where the derivative is pointing, since the derivative is pointing to the left, that tells us that we actually are going around in a circle such that we are going in a counterclockwise direction, anti-clockwise direction. We're just not starting over here. We're actually starting down at the bottom. So if you're on a circle, if you're traveling on a circular path, your r prime is always orthogonal to your r. And for those of you taking physics, you already know this, right? When you've got uniform circular motion, your velocity vector is always tangent to the curve, right? Yes, no, maybe so. There's only centripetal acceleration. There's not any tangential acceleration. Anyway. All right, so cool-ish, not too bad.
Is
All
there
right,
a
well,
quotient rule?
Okay, so is there a quotient rule? Good question. What do you guys think?
Probably.
Probably.
You can just
bet it's
invert
really
the
painful.
multiplication rule.
God, I hope not.
Okay, so do you want the good news or the bad news?
I want just the truth.
Yeah, both at the same time.
Okay, so here's the reality. The reality is, it's all good news. There is no quotient rule, which you might say is bad news, because then you're like, well, shit, what do we do when we divide? But that's why there is no quotient rule, is there is no such thing as vector division, right? You can't take R or V and divide it by U, like you can't. So since there is no vector division, there is no quotient rule for derivatives.
Okay.
Yay. So good news and bad news, right? I guess the bad news really is you can't divide vectors, but I guess that's also good news. It's one less thing that we have to do. Right? All right, so we feeling pretty good about differentiation. It's just same thing, just more of it. And you'll see that when you go and you work on the homeworks. It's basically each homework problem is 2 or 3 homework problems from before, right? Because you have to differentiate each of the individual components to get where you need to be. So.
Do you mind going over space curves?
Not at all. So, like if we have a space curve, this is when we've got a 3-dimensional vector value function and we're trying to plot the parametrics. Let me give you an example of one. Let's bump one of these suckers up to 3D. So this is probably a similar example to what they do in the book, because this is the easiest one of these to picture. Well, let's just say that we've got this as our vector value function. So let's just kind of look at each component and see what they're individually doing. Okay, so the x component is following cosine of t. So at 0, we get 1. I'm just going to kind of follow along this graph with my finger with the x. So x starts at 1. As t goes on, cosine goes to 0, down to -1, to 0, to +1, and just keeps alternating back and forth. So whatever this looks like, the x's are just going to keep going back and forth like this. The y's are doing something similar. They're starting at 0, going up to 1, back to 0, down to -1, back to 0. So it's now, if you were to put those together, what we would see in terms of x and y is this, right? So forget about the z for a second. If you just looked at x and y, we're going around in a circle. This is the parameterization for a circle. So those two components, they're just going to do this. Now, what's happening with the z?
Going up at a slope of 1.
Okay, so it's starting at 0 and it's coming out, right? So at t = 1, t = 2, t = 3, t = 4, and so on. All right, so think about this. At 0, we're right here at t = 0. We're on this portion of the circle, and we're on this plane because t is equal to 0. As t progresses, I'm going to start rotating, but I'm also going to be coming out of the board. So that by the time I'm above this point right here, so pi over 2, right, 1.57, my z is 1.57. So I started here, and I've come out this far. And then I continue to come out further and further as I go. So what this is a helix. What you're going to see like from the side is this. So this is z going up like that. So we're going around in a circle, but as we're going in a circle, we're getting pulled away. So these are actually really, really tough to draw, right? Like if you're just going to try to draw one on your paper or on the whiteboard, it's a little bit difficult. But there are some really good plotting programs to do this. So let me share my screen real quick, and I will show you one. So I think where I want to go here, well, let's see what Desmos does. Desmos is my go-to for graphing. Let's see if it does a 3D. This is also really good if you want to graph parametrics, even in 2D. So we'll start with just a 2D one. Right, so you can see how this is giving us the circle, x is cosine of t, y is sine of t. Let me try putting on a third variable here. Well, no, it doesn't like 3D. All right, well, ignore my recommendation of Desmos for 3D. The other place I like, yeah, you can change, is CalcPlot 3D. Oops, that's not where I wanted to go. I don't think. No, yeah, I guess it is. This is a really good 3D plotter for surfaces. I don't know that I've ever tried to do this for a curve. So let's see if we can figure this out. We'll get a lot of practice with CalcPlot 3D in a couple of, in a later chapter. Let's see. I'm going to eliminate this. Someone's chatting at me. Hold on. I got to pull up my window. All right, so in add to graph, oops, okay, hold on. There we go, space curve, boom. All right, so, and this one's pretty much set up the way we want it, right? Cosine, sine, and t. And so now you can see that helix coming out. Let me adjust the scale a little bit on this so that it looks a little bit more like what we want. I'm going to go with their recommendation of just scaling this down. Let's go 0.1t. All right, so now you can see the spiralness of this guy. And so this was where we were at time equals 0. 0x, 0y, 0z. And as time went on, we started going around in a circle, right? Like if we look at this from the top, it looks like a circle-ish, right? Close enough. When we look from the side, you can see that z going up. And so if I tilt it just a little bit, you can kind of see the spirally nature. So my advice, if you've got something funky and you want to get an idea of what it looks like, come to something like CalcPlot 3D, draw your space curve, adjust it so you get a feel for what's going on. But I literally do what I started with. I look at the individual x, y's, and z's, and then I figure out what they're individually doing and kind of piece that together in my mind. So anyway, that's my big suggestion, is go to something like CalcPlot 3D. Plus it's just fun to play around with. So does that help, Bradley? Does that make some sense?
Yeah, definitely. So when you were dealing with all sorts of different geometric shapes with space curves, do you think it's wise to look at it parametrically, just individually like you did?
Absolutely. I mean, it's what I do. It's my go-to. So yes, it would be what I recommend, but if there's a better way for you to see it, then do it that way.
Okay.
All right. So I see we're just about done. We've got like 5 more minutes, but I think I'm going to go ahead and stop. Let me just do something here real quick.
We're going to go ahead and switch screen view so you can see me again. But anyway, so now that we've seen how to differentiate, obviously the next step is how do we integrate? But before we get there, we're going to talk a little bit more about this tangentness. And there are some vectors that are kind of useful that come from this that we're going to use later. One of them is what we call the unit tangent vector. We need to wrap that up before we move on to the unit normal vector and things like that. But once we get integration down, and spoiler alert, it's just like regular integration, just more often. Once we get that all down, we've got these tools, then we're going to start using them. And one of the big things we're going to do is look at motion. We're going to look at 3-dimensional motion, how we can use vector valued functions to describe it, and then how we do the calculus on it. And this will bring in a lot of the stuff that you've done in physics. It's just going to allow us to go to 3 dimensions which was kind of a restriction that you had last year, right? Anyway, so that's where we're going, and that's what we're going to do on Friday. So I'm going to go ahead and stop the recording here.